Why?
Because whenever I ask a question, I can hear myself.
Isn't that better?
It's incredibly annoying.
Your voice isn't annoying.
It's annoying to me, especially.
Well, of course, everybody's voice is annoying to themselves. Okay, we're recording. I don't know. It's like you write and you look at your writing and like, if you really critique your writing, I don't like the way I write. Really? I have to work.
Really? Because I think it's crap.
All right, questions before we review. First one of the homework you said? 20.21?
Yeah,
the first one.
20.21.
20. Why do I need to? Is this one important?
This one was just, it was interesting.
A 20.21. Didn't we do that one? Sketch the PMOS equivalent?
Well, you did one
The
of them.
first one for figure one.
But, so, like, the resistance is, can you just, like, do the resistance of one of the short channel ones, either 38 or 42?
Okay, so what specific question you want me to do?
We use sim 2038, but you have to do it as a
2038, and it's PMOS. Is this problem going to challenge me, or I'm going to be like, crap, they're not learning?
I hope it doesn't challenge you.
All right.
Challenge
2038. I'm going to cheat on this one because it's so easy. All right, we all good to go? So how am I going to cheat? PMOS equivalent. So I'm going to go over to the LT Spice for chapter 20. Then I'm going to go to figure 2047. And then I'm going to say file save as what?
Just a random.
Figure 2027 desktop, and there's our, and this is lecture 15. Is everybody cool with that? So we don't need a lot of the stuff here, so we don't need the this stuff here. So I'm going to get the scissors out. Is it okay if I cut this Lito? Oh, where's Lito? Oh, he's not coming to class. He must be ready for the test then. Good. We'll make sure we review part of the lecture off without the video going. All right. So I'm going to get rid of these because I don't need these. Would everybody agree? Well, it's not part of the homework problem. I don't need any of them. Well, hold on. Maybe I do. What's the craziness? Come on. Okay. So I'm going to get rid of these. Boom. Then I'm going to get rid of these because I don't need those. Oh, wait. Is this the one I need? What was the problem again? I already forgot. Oh, 38. So PMOS equivalent. Oh, all right. And so I do need these. These are connected. I don't need V high. So let's get rid of that. That confuses me. And I do need this one, so let me stretch it so it looks exactly like the figure in the homework problem. So let me get out the scissors here. And then let's go here. And then let's see. I guess I don't really need the V bias, so why don't I get rid of all this? Although you could use this for your other problems. Let's just get rid of this. Boom. Sound good? And then let's go up here and go V bias N. And whoops, you know what? Let's do instead. No, let's not do that. Let's go V bias N and plop that down here. Then let's right click on this and go V bias N. V bias N. Let's get the scissors out so it matches the figure. Then let's get this out. And then let's go ahead and stretch this up. You want? We can move it over here so it's easier to print. All right, so far so good, but we're still not there because in the figure, figure, we have the PMOS equivalent, which is the output. So we have those two NMOS and then the 3 devices there for PMOS. Those two NMOS, the 3 devices now PMOS. And then I need to get the copy out and go over here. And then I need to connect these over. Boom. Boom. And then I need the output resistance. Is that what it's asking for? Okay, so let me go get a voltage source and say OK. Plop one here. Plop one here. Press G. Boom. Boom. And then label VDD. Is this boring, everybody? Because it's so easy. Does it look easy when I do it, or does it look hard? Oh, 1 volt, thank you. What's that?
I don't know though, because that would have been, that's the BMR thing, right? So
Yeah.
it's already been set to 1 volt.
Yeah, but you have to power it externally. I want a DC value of 0 and an AC amplitude of 1 millivolt. Hit OK. And let's right click on this node just to make sure they're all connected. And they are. Any questions before I simulate?
Your top circuit is just your bias circuit.
Yeah, it's just a BMR.
Okay,
So that's the homework.
Why did you do AC?
Because you wanted output resistance, right? You're going to kill me if you ask how come you use AC for output resistance. I'm going to be like, are you kidding me?
You're gonna cry on this.
All right, I probably will. All right, why don't I make it easier because you guys don't like the BMR, so the homework problem didn't say you had to use the BMR, so let's get rid of that. Did it say use the BMR?
It was already in there. Yeah.
All right, so you want me to use it?
You have to, don't you?
Okay, yeah, sure, I don't care.
Well, if you don't use it, isn't it gonna change?
No, I'll just make a gate drain connected NMOS with a 10 microamp current source over here, and I'll generate the V bias. Get the same thing. Because in the simulation, I can use an ideal current source. Are we ready to go? All right, so what's the sim I'm going to use? I'm going to do a dot AC decade 100 points. How about 1 kilohertz, 1 hertz to 1 kilohertz? Okay. Boom. Where's my dot include? Plot CMOS EDU models. Do I have that on here somewhere? Dot include. It's easier to use the schematics, and in fact you can directly use these right here from the figure. I mean, I didn't even have to do all this extra work. I'm just trying to show you that, yeah, you can do it. It only takes a few minutes. But I mean, if you use this figure right here, the bias circuit's going to be exactly the same as what I just drew. Okay? So dot include CMOS edu underscore models dot txt. Boom. Hit save. Hit run. Let's make sure we get a nice current flowing through there. How much DC current do we have? Oops. 11 microamps, close enough. Let's plot the AC voltage. And then I need to plot the AC current. Well, let's go over here and do linear. Actually, let's make it nice. We want the grader, me, to enjoy grading the homework, not wonder what the heck. So let's right click on this. Whoops, hit cancel. Let's call this, right click here and call this VTest. Then I'm going to label this node VTest. And then I say to myself, hey, the current that flows in this is going to be negative because SPICE defines positive current flow from plus to minus. So I could put a 0 volt voltage source in there, or I could just use the minus. So let's hit run, and then let's go and do it different. Let's click here, and let's plot I of V test. There it is. Let's change this to linear, and then let's put parentheses V of V test. There's so many examples, I mean, of plotting output resistance. And you mean you give me examples, you want me to look at them? Yeah, so it says 12 meg. I'll hit save on there, and then I'll go back to the book. And let's just compare what I just did there to table 9.2. And GMR out is 25, and R out is 167. So what's 25 times 167? Why did I say that? I assume everybody knows why I multiplied GMR out times R out to get GMR out squared. Why did I do that? It's the output resistance of the cascode is approximately GMR out squared. Don't say, really? Because we've derived it like a half dozen times, right? So what's 25 times 167K? Pretty close to 12 meg, I'm guessing, yeah. But I could also go back in the end of the chapter, because I am reading the book, because I'm going to handicap myself if I don't read the book. And I'm going to go to the table here, and I'm going to look, and I see my short channel, just the regular cascode, is 16 meg for the PMOS. And I use the wide swing now, so that's the regular. I use the wide swing. It's going to vary because of Y. I'm changing the drain to source voltage across this top device here. Yeah, remember in chapter 9, one of the big deals we did was we said, hey, when we get output resistance, it's not going to be precise for the nanometer device, because look at this plot. And we went over that. And we said, wow, where is it? Wow, look at this. If the output, if the voltage across the device changes a little bit, the output resistance can change by an order of magnitude or more, factor of 10. So when I get variations in the output resistance, I know it's going to be related to the drain to source voltage. I know what you're thinking. He's only gone over that 3 times before, and he expects me to remember it. What's wrong with him? Just joking.
So when you do the reciprocal of the derivative of the ID?
For an AC analysis?
I don't know, that's what the book says to do to get your...
That's not for an AC. What analysis is that for? Yeah, DC sweep. Let's redo it.
To get your R out.
Yeah.
Then why are you talking like I was crazy whenever I did DC?
The way you said it. No, you said I'm going to look at the DC. You didn't say, when you say look at the DC, I'm thinking dot OP and look at the DC operating point, not sweeping the output, doing a DC sweep. So let's do a DC sweep. So let's go over here, and let's, what do I sweep DC to? Or what do I sweep here? What's V out? That's right, VT. And we're going to sweep it from 0 to 1. And what's going to happen as we get close to 1 volt? Yeah, the output resistance is going to get small. I hit OK. Then I hit, oops, do not do that. I almost made a mistake. And I hit run. Then I go back here and I plot the current flowing through there. Then I go derivative. Because it defines positive current flow going the other way, so let's just put minus. And it sees, hey, as we get closer and closer towards the power supply and the current source shuts off, our resistance drops. And that makes total sense to me because I understand what I'm doing. Any questions? Was that homework problem challenging?
Yes.
What? You got all of the examples in the book. I mean, basically, you're just using the examples from the book. They're already drawn. Your simulations are already there. I feel embarrassed asking you such a simple question. Serious. They just have to modify some, they don't even have to modify the existing simulations. They just need to press the run button and plot. All right, any other questions on homework? Any other questions from chapter 9, 20, or 21? All of them? So does everybody see the next homework? Yay?
Only 2 problems? Really?
I don't think that's right. I think I meant to write 21.1. Yeah, I did,
No,
actually.
I
Thank
don't
you.
think so.
Yeah, I did. Let's fix that real quick. You can see how I do it. What's that?
Sorry, got excited.
No, that is wrong. I don't want you to think that you're getting ripped off. I don't want you to, right? I don't want you to feel cheated. Let's see. Boom, there it is.
Are you sure?
Yeah, yeah. Okay. So,
I had a question from the last lecture.
yeah,
You were doing, common source amplifier,
yep,
and when you were deriving your gain,
yep,
there was a point where we had our gain AV equal to, 1 over GMP parallel RL parallel RLP
yep.
over 1 GMN, and you said that we use 1 over GMP over the 1 GMN. Why do we use that rather than RL?
Let's do it, man. So would you agree that I can model, let's do the PMOS. Would you agree I've got a current source there for the PMOS, so I modeled that part as GMP times ID, and that's R out P. Would you agree with that? Is anybody worried about the test? Is it poor instruction? Is that why you're doing poorly on the homework? Lack of online resources? Lack of examples to look at? Lack of time? More PowerPoint?
Yeah, definitely.
All right.
You can have it fly in here, right?
Does people do that?
Yeah.
Okay, would everybody agree with me that I can model the transistor as a current source in this? So I'm going to write the, how about let's just look at this part right here. Would everybody agree that I could write, we'll look at it in superposition. This is GMP times ID, and then my source. If I connect my, this is my source, and if my gate is here, and I tie my gate to my drain, then I've got this, correct?
Sorry, why did GMP times ID?
You're killing me. Why is it GMP times ID? Oh, sorry, I'm killing you.
You're killing me.
Yeah. Yeah.
Why didn't you tell me?
Officially.
Like all over the
Because, you just sounded so sure.
I was like, there's no way.
Even I was just like, oh god, I missed something.
How's that?
Wait, there's one more. Yeah, one more.
One more?
Your other current source.
Oh, past performance is the best indication of future
I think we should just
performance.
start all
I
over.
almost did.
No, we're not starting.
There's no way he read it wrong 3 times.
All right, so let's say I ground the source here, and then I apply a test voltage, V test. So tell me what VSG is in terms of V test. I don't have a resist. I'm doing just this part, not this, superposition. Okay, so what is I test? Oops, wrong way.
GMP
So wouldn't everybody agree that V test over I test is equal to 1 over GMP? So wouldn't everybody agree that when I go put my resistance, if I say what's the resistance, I ground this, what's the resistance looking into the drain due to the output resistance? Yeah, it's ROP. Does everybody agree with that? So when I model the transistor, I model it like this. Would everybody agree that this is AC ground? Can't change that voltage? Would everybody agree VSG is equal to minus V out, VAC?
Yeah.
Would everybody agree that I have plus minus V in is equal to VGS? So I'm going to redo this guy as a 1 over GMP in parallel with R out P for the AC circuit. And then here, I'm going to have a current source, which is GMN times V in. And shunting that, I'm going to have a V in, and this is R out N. And these, of course, are shorted together. That's the source, drain, drain, source. So far, so good. So would everybody be cool if I rewrote this is questions? So here's where I cringe. What's V out? This is where crappy Circuits 1 education hurts you. And what is that voltage? This should be like, you should have this down like within a month of Circuits 1. I mean, it should be like, I'm taking a drink of the soda, so it's negative pressure. The current's flowing the other way, I'm blowing bubbles into the soda, it's positive pressure. This should not challenge you. So what's the voltage V out then? Oops. Well, what's R out? It's like mega ohms. What's 1 over GM? It's like kilo ohms. You're talking 1,000 to 1. Look in tables 9.1 and 9.2. That's transistor. If that's not the case, then remember our GM R out is R out over 1 over GM. If this isn't, if R out's not much bigger than 1 over GM, then our transistor has no gain. Has to be greater than 1, much, much greater than 1. The bigger the better. That's our open circuit gain, the transistor driving its own impedance. Questiones? No pregunta? No? Everybody understands. Does that make sense? You're taking a lot of notes back there, man. Yeah. Is that because my notes are chicken scratch?
I learned from half of mine.
What's that?
I learned by doing half of mine rather than years of mine.
Oh.
Better when I write.
Do this. Just sit back and trace over. That would be really good. When I'll take pictures of you, my students freaking out.
I'm memorizing something and I'm like, I'm getting that one right now.
They're gonna be like, that dude's crazy. And then when they drive up next to you, just go. Come on. All right. Let's review for the test. Before I do, are there any more questions? I'm going to tell you what to review. And if you've taken classes from me before, I don't try to, well, I don't know, you can ask other people. I don't try to trick you, but you actually have to know the material. Okay? And so don't think, oh, I'm going to get through and it's going to be everything. No. I'm not going to ask you hard problems, but if you can't get them, you're not making it. Okay, so first off, I want you to know the IV plots. So let me give you an example. Plot I versus V. So in other words, study your homework and quizzes and end of chapter problems. You need to do this for all of them. What's that? Two Z's? Oh. There. I forgot to spell use one time. I mean, things fall out of your brain listening to too much music. That's my issue.
Be honest.
All right. Any questions there? Do you want me to work any problems? Why don't we finish and then think of anything you want me to cover, and then we'll do that. Okay. So the IV curves. Like here's one. Okay, here's what's in my mind if I ask you this. What? I'm thinking this will take them literally 5 seconds. They do this. What does the plot look like? If it doesn't take you 5 seconds, if you need to look it up, if you need to think about it, you know what? Man, that test was long. Let me show you a variation on that one. No, I'm going to make it a little more challenging than that. What's it? Well, wait, do I need a ground here? Let's talk about that in a moment. The answer is no. Let's plot VSD. What does the plot look like? If VSD is 0, what is this potential? If VSD is 0, what is this potential? 5 volts. Right? Because if VSD is 0, it means you put a wire there. A 0 volt voltage source is a wire. So it's 5 volts. So what's the current that's going to flow if both sides of the transistor at the same potential? 0. So what's the plot look like? See, this is what I'm talking about. If you don't know these and I ask you, it's going to take you 10 minutes on the test, and man, that test was long. No, you didn't know what you were doing, and I asked you a trivial question. ID versus VSD. VSD is 0. Does everybody follow that? Anybody not follow? How do I know? If VSD is 0, there's 0 potential between the source and the drain. There's no current going to flow. Because I don't have any reason for the current to flow. Both sides of the device are at the same potential. Okay, so now before I give you a modification of this, let's say I put a ground right there. Oh, sorry. Okay. How much current flows in there? Anybody not agree with that? What's the relationship between the current here and the current here? The same, right? Okay, so where does that current come from? It's going to come from here. So how much, oh wait a sec, I don't agree with that. I think some of the current's going to come from here because after all, even though you're being lazy, those are connected just like that. So I think some current's going to come from this source. Oh, really? So if I put this as 0, this shorts this to ground and it doesn't work, right? So I can't have that because then I'm shorted this to ground and I get an infinite amount of current to flow. So that won't work. So if VSD was 3 volts, what would be this potential here? Oh, wait, that doesn't work either, does it? Because this would be 2 volts, and then I'm saying these are shorted together. So I can't have that because if I put the ground here, and this is at 5 volts, then I can't change the VSD. So I don't want to do that. Okay, so now, let me go back and do the exact same problem again, except I'm going to modify it. And you're going to tell me what's the difference. Oops, I didn't want to do that. Let's just call this Vx. And I say plot ID versus Vx. This is straight out of the current mirror problems that we did in chapter 20. Okay, here's how you approach the problem. You go for the simple stuff first. What's the most simplest thing I know about Vx? Let's say this is 5 volts again. This is VSG greater than the threshold voltage. What's the simplest thing I know? No, simpler. When Vx is 5. No current at Vx equal 5. But as this voltage starts to drop, what happens to the pressure across the device? It goes up until I reach saturation and I flatten out. Because I know at 0, in this exact same circuit, I've got 5 volts across here, and I've got a current flowing. But I'm going to know these backwards and forwards. What are some variations? What is this one if I plot ID versus VGS? Turn the valve on. Let me show you a variation of that. Let's say I ground right. Wait, let's see, where do I want to ground here? Doesn't matter. I have to ground somewhere to make it reference. It's going to depend. You do both problems. Ground right here to begin with. Let's do that one, and then you could also ground up here. Tell me how to approach this. You need to keep things very simple. This is at ground, so what do you know all the time? VDS is constant, and what's that voltage? Always. And you know this voltage has to be at least a threshold voltage below this one for the device to turn on. So you know if I plot ID versus Vx, when Vx is close to 5 volts, I'm going to get no current flowing. Then as Vx drops and gets smaller and smaller, I'm going to get a curve that flows like that. I will ask you one of these problems. I will ask you an IV plot problem. Any questions? You have it on video. You can tell me I'm a liar when I give you the quiz and that's not on there. Of course, I won't be lying. Questions? Is that bad? What time did you get off work? What? Oh, that's right. I was thinking yesterday was Sunday. I'm so used to Monday, Wednesday classes. All right. Any other questions on this? What do we talk about next? Nothing. We didn't learn anything in this class. What's that? No. Yeah, those equations, but we also talked more about small signal parameters. How to derive and use GM and R out. So let me give you an example. Show how to derive the transconductance of the PMOS transistor GMP. What do? I'm going to do it for you. You do the following. Got to have a pressure there. I could do it other ways. Just say big because I just want to make sure it's in saturation. Big means VSD large enough so the device is in saturation. Let's call this VSG. Is everybody cool with that? Then I know there's a DC current, ID, plus an AC current, which I don't add into one number. And I know that if I bias from the previous problems, ID, VSG, that as I increase VSG, I'm going to do the following. When I wiggle VSG, I'm going to move back and forth. 1 over that wiggle is, or the ratio of that wiggle, the del ID, del VGS, is GM. So then you go, oh, that's right, ID plus little id equals Kp sub p over 2 times W over L times VSG plus little VSG minus V threshold P squared. Need to find the slope there. So GM is defined as the derivative of ID. And what is ID, this little ID equal to? Yeah, AC plus the DC. At that point. And that's equal to, what's the derivative? The 2 comes down. I get Kp sub p times W over L. How was your calculus education? Okay, that's not what I like. So when I take the derivative, I have to take the derivative. This is VSG. So derivative of that is VSG plus, I'm sorry, the derivative of what's inside here is VSG, or not what's inside, I'll do that in a moment. And then the 2 came down, and then it's times the derivative of what's inside here with respect to VSG, and what is that? What's the derivative of x minus a with respect to x? 1. And so the derivative of what's inside is 1. And so then I say, what was my small signal approximation? This didn't wiggle very much, so it's linear. So tell me what to do here to get 100% points. Small signal approximation. And then boom, there's my GM. Took me what, 3 minutes? And it's open book. And you know what I'm not against? You writing in your books. Write lots of stuff there, Warku. Write you, this class is painful. Write yourself reminders. Pick up milk and eggs on the way home from school today. And my grocery list. All right, any questions on small signal parameters? Now, what could we do that I'm not talking about? R out P, how do you drive R out? GMN, how would you derive that? And then in the current mirrors, we did output impedance. What's the difference between deriving the output resistance of a MOSFET and the output resistance of a simple current mirror? That's right, absolutely nothing, because the output resistance of a simple current mirror is R out. Any questions on small signal parameters? Do they make sense? Did they make sense in 320? They make sense in 320? All right, be honest, that's good. Do they make sense now?
Yeah.
Okay. You turn the hose on, that's your DC bias, and you wiggle it back and forth and look at how much AC flows.
What kind of dots sound like what?
You're killing me, I don't believe that. No one would accept a paycheck and not show up and do the job. Okay, good to know. The last 5 years here will be great. No, past performance is the best indication of future performance. All right, what do we talk about next in Chapter 9? Was Chapter 9 full of info? What do we talk about next? Based upon GM, GMR out, GMR out FT, those kind of things. I want you to know What influences FT? Short question. What influences FT? Oh, I need to go look in the book. You're burning time. Yeah, length and overdrive, right? Or here's one for you. Why doesn't width influence, in your own words, why doesn't width influence the FT of a transistor? It cancels out in the equation? No. If you increase width, what happens to GM? Okay, let me give you an example. If I increase the diameter of my hose, and then I've got a bigger valve obviously because I got a bigger diameter hose, and I turn by 1/8 of a turn with a bigger width hose versus a smaller width, what happens to the amount of water that flows for the same 1/8 turn? You get more water with the bigger pipe, right? Same thing with the transistor. You increase the width, you're going to get a higher GM because you don't have to apply as large a VGS to get more current variation. One more time. Let's say that I've got a 1-inch hose in my yard and I bias it on and then I turn it, the valve 1/8 of a turn, and the water changes by 0.1 gallons per minute as I wiggle it back and forth. So in one position it's 0.9 gallons, in the other position it's 1 gallon per minute. Okay? Then I go to a 3-inch diameter hose and I turn the valve and it goes from 9 gallons a minute at the smaller to 10 gallons a minute. Because I've got, even though it's the same 1/8 turn, I've got a bigger diameter hose. It's that simple. Now I increase the width, what happens to GM? It goes up. Because I got a wide, that's exactly what's happening. I got a wider width in my channel, I got a wider hose. But what happens to the capacitance of the device with the wider width? Remember Cox is equal to Cox prime, which is epsilon ox over Tox, the parallel plate capacitor, times W times L. It goes up. So my GM goes up, but also my inherent device capacitance goes up. And they go up by the same amount, so the ratio stays the same. So the width doesn't influence the FT. Does everybody follow that? What about GMR out? Make sure you know those, all right? Because I will ask you something there. How do I get large open circuit gain and why? Use your own words. I'm going to answer this because we're running out of time and we do want a quiz, right? What's that? Yeah, but why? I mean, if you go into a job interview and they ask you, I mean, and by the way, I got the Spectrum a few days ago, which is the IEEE magazine. There were literally 1,000 jobs in semiconductors in that magazine at the end of the magazine. Okay, and circuit design and all that. 1,000 jobs. Most of them, I just saw the Intel jobs and I'm like, holy crap, they're hiring like crazy. If you go to a job interview and they ask what happens to open circuit gain or the transistor's inherent gain as you reduce the current. And you say, it goes down, reducing the current, the gain goes up. They're not going to say, oh, that's right, let's move on to the next question. They're going to go, oh, they answered that quick. Let's see if they have any depth. Why? Because you're going to be an engineer, not a technician. Engineers need to know why. Technicians need to follow orders and know what to do. Tweak this knob, this happens, all right? So the answer is why. Why does the gain go up with decreasing current? You can go and you can use equations. I can answer it verbally. I'm going to use equations. Output resistance is proportional to ID times lambda. So if I reduce the current, I get a linear change with output resistance. GM is proportional to the square root of ID. Everybody follow that? So when I look at this, I go, my change in GM is slower with ID than my change in ID. So the product is going to go up with reducing ID. You know, the job thing, for me, that's the whole reason of going to school, is to get a good job. And there's going to be a lot more opportunities in Nevada, mainly because of the tax structure and what the companies that are moving in. And the only thing that I found, you might think, oh, well, I got this bad or this is bad. There's bad things at every school. But you know what? If you go to MIT, you're like, I went to MIT, and you have self-confidence. So you have to have self-confidence, and you have to be able to go out and go, I'm doing this, and I'm going to go get it, and I'm going to see what I need to do, and I'm going to make my resume good and all that. And that's the only difference. Because you think you're learning a lot in school, but you don't learn a lot until you actually get a job and you do stuff, all right? That's why I'm a big fan of hiring people that have industry experience, okay? Because you actually have done the job. No, I'm not a fan of hiring people that just go straight through school as professors and don't have industry experience. All right, any questions on this? Because we got 20 minutes. We won't have a quiz today. Are you bummed?
Synopsis, you said the change in GM is slower than the change.
Yeah, so when you look at the product, this is linear, this is square root. So then as you reduce the current, you get an increase. So ID go down, GM R out go up. Questions?
So,
Yes?
to get more gain, we play with the length.
You can
So
do
adjust
something with the
speed
length.
also?
Yeah, make sure you study that section of the book and the past videos. But for, if they ask what happens to GMR out with ID, this is true. For the length, that's the only parameter you can adjust both the speed and the open circuit gain. So the GMR out FT, GFT, this is the GFT. Know how that changes with length and overdrive and all those things. That's, yeah, you look at it, and I think I've covered it great. So you tell me. We'll have some short questions on that stuff. Any questions before we leave chapter 9? I got a question.
We have to do 9.5?
Yeah. Study example 9.5. Here, let's do this. Study quizzes. Notice 2 Z's. It's not Z-top, it's ZZ-top. Study quizzes, end of chapter problems. I can't imagine how many people are going to go, who's ZZ Top? I'm like, oh boy. I think it's already happening. Quizzes, end of chapter problems, and homework. Yeah, if they're useful. I don't know if they're that useful, lecture videos. I'm lazy. You know I'm lazy. I will go in and take homework problems or quiz problems and put them in, maybe with minor modifications, so it only takes me an hour to write the exam instead of 4.
Saying you haven't written it yet?
No, I have not. I've been busy, man. I've been really busy, actually. And I don't mean busy lounging by the pool. All right. What's that?
So that's like 2 questions.
What is?
What we just went over.
The chapter 9 stuff? I
Yeah,
don't
there'll
know.
be 2 questions on that. What we just went over.
Maybe, I don't know. I'll think about it when I write up the test. How can I challenge them so it builds their self-confidence but doesn't break them down? You want to plant the tree and expose it to the wind in a little drought, but not so much that the tree falls over and you...
I don't know if you can put it back, like, why did it look like that? Like, not like that.
This-
More like an arc, instead of going the other way, like,
This one?
yeah.
You're reading the book, right?
Quick question.
Let me answer his first, man. See the PMOS current source right here? So when this node goes to VDD, what's the pressure across there? 0. So as this node drops from VDD, then the current increases. It's all there.
So right there on that page.
Yeah.
On the bottom left, that VX where you have the ground.
Yep.
So then on the next page, that curve, if you had that ground, that's the same. Oh no, I see. Never mind.
All right. So let's move into chapter 20. And one big thing that you need to know in chapter 20, the two biggest things are the DC biasing and output resistance, I guess, in topologies for three things. So let me give you a circuit. This would be a great problem for me to give you. It's not in the book. Let's do this, just to be complete. And this is one maybe I shouldn't do, so you force yourself to do it, because it's not hard. Unless you want me to do it for you. No?
Yeah, but you should probably write in different
How about I do some of them? Then I leave some to you. How about I do this one? What is this voltage here and why? Oops. Gee, I'm really blowing it. Okay, does everybody agree with that? Why? VSG is what? VSD sat plus V threshold P. So VDD minus VSG is this voltage here, because the VSG is VSD sat plus V threshold P. What is this voltage here? I'll start you out. It's a wide swing current mirror. I hope everybody recognizes that, right? I don't need to tell you that's a wide swing current mirror, right? So what is this voltage and why? So what is this voltage here or this voltage here? Because what's the voltage here? VSG, which is VSD sat minus or plus V threshold P. If this takes you 10 minutes, you won't finish the test. The English 102 class will come in and I'll have to leave and you won't get a good grade. Because this shouldn't take you long. Should it? It should. Rudy? He's going, oh, no, it'll take long. I'm being honest. Okay. Output resistance, do I need to do more of those? PMOS, what's one that you haven't really studied that you should study? Yeah, the amplifier one. So just tell me, knowing how I quiz and what we've gone over today and other times, what do you think I might ask? Sketch the schematic of the PMOS current mirror using regulated drain topology. Show how to derive the output resistance of the topology. Well, let's see if I can find in here the PMOS version. There's the NMOS version. Would it be a challenge to sketch the PMOS version? I think we even did the PMOS small signal output resistance in class. Wouldn't that be reasonable? No.
I could use more practice on the PMOS, sketch PMOS.
Do it real quick.
Yeah.
Again, even though it's recorded in videos, and that means we don't need videos, just your notes are enough. Okay. Should I use the book and cheat? I should.
So this is basically the same, you drawing the amplifier there as the circuit, I think it was like 20.42 maybe, where it's got the two resistors, or transistors facing out that goes in between that one and goes in between that one. I think it's 20.42.
Yeah, that's, yeah.
Except for that shows the transistors instead of like this amplifier.
So here, poop. Thank you. I don't need that pill. No.
Yeah, look at
1, 2, 3.
20.42.
1, 2, 3. 20 point what? This is the amplifier for the NMOS.
Right, but that's the same schematic, right? You're just showing
No.
your.
I'm doing the equivalent schematic of, oh well, someone will
Well, you're doing
smash
the
that.
PMOS, but I'm saying that's instead of the
No.
amplifier symbol.
So this MA1,
Those two are your.
that's this. Yeah.
Okay.
All right. We're running out of time here. So what do I do? Is everybody cool with that? So why don't I do the following? Let me kick it into overdrive. Well, first off, this would be a problem I would put. Sketch the PMOS equivalent of the regulated drain cascode current mirror shown in figure 2040. Label the voltages in terms of VDD, VSD sat, and V threshold P. Show how to derive the output resistance, 25 points. Okay, so what's this AC voltage? What's this AC voltage? Okay, so what do I replace this transistor with? R out P. What's the current that flows in there? I test. This voltage is V source, so V source equals I test times R out P. What's the output voltage here? Right? So what's VSG of that transistor? This voltage, I test times R out P, minus this voltage, which would be A times I test R out P, is the VSG, which is equal to I test times 1 plus A R out P. Okay, so then I come over here and I go, oh, that's a current source of I test times 1 plus A R out P. There's my R out P. There's my V test. There's my I test. Now I've got the same old thing where I just do the algebra and I could do a KCL right there, knowing this node is I test R out P and this node is VT, and plug and chug. Yes?
That current source should be.
Oh yeah, GMP. Thank you. All right, we have 4 minutes left. Sketch the PMOS equivalent of the regulated drain current cascode current mirror seen in figure 2040. Label all DC voltages in terms of VDD, VSD SAT, and V threshold P, showing how to determine the output resistance of that current mirror. Okay. What else did we learn in that chapter? That's enough. In 20. What? How about matching? No, that's too much. You're testing this over too much material. What's the most critical thing for matching and why? Just one sec. No, you don't. VGSs are generated. They don't change. I mean, they're assumed to be the same. You change your VGS, you're not going to get good matching. It's current mirror. They got to be the same. Just a sec. Let me read in the book about matching because I haven't been reading the book as he's repeatedly told me, and so now I need to read it during the exam. Man, that exam is long. What is the most critical thing? We went over this in class for matching in 2 current mirrors. It's a theme that we use throughout this semester. The size and the VGS, they got to be the same. VDS, we got to equalize the drain to source voltages across. That's the whole point of us adding that extra device in the wide swing current mirror, so that the currents would equalize the VDS. And then you need to be able to articulate, if I ask some minor variation, why the VDS is important. Fix the VGS, which is a given. You can fix the VDS, then your ID is going to be fixed. Everybody follow that. See, anything else big thing we talked about a lot about in chapter 20? Operation, topologies, all those ones like in the study session on Sunday that we did. And how about startup circuit and qualitative questions about operation? Looking good? Stuff we talked about. What happens if you put a capacitance across the resistor in the BMR? Can oscillate. That's a big section in the book. Potential problem. Okay. Finally, what was the last thing we talked about? Here's one. let's say this is 1.05, this is in the long channel process and it's 10 by 2, this is 1 millivolt, this is 100K, this is 2 volts, this is V out. This is simpler than the ones using the transistor loads, but I don't need to do any calculations. What's the current that flows in the device based on 1.05 VGS long channel 10 by 2? VDD is, oh sorry, I'm getting ahead of myself, 5 volts. 20 micro. So what's the voltage drop across 100K? What is the voltage drop? 2 volts. So what's the DC output voltage? 3 volts. How much AC current flows? Assuming the 100K is small compared to the output resistance, which it is, then V out equals minus 100K times 150 micro times 1 millivolt. Oops, we're over. Any questions? Have a good day. We'll make sure we have a challenging test for you on Thursday. Unless you tell me not.